Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody on YouTube watching us from the future. Welcome Tobias, who will moderate today's lecture. So what's the plan today? I will finish this about HDFS because we have this cliffhanger on the single point of failure with the name node. So this is the last bit we need to discuss. And then we'll look into syntax in the world of big data and why does actually syntax matter. But before that, I have a few questions for you. Here. So this is my first question. So Dynamo or DynamoDB, which is implemented on the name of the product, is it consistent, available, or partition tolerant? You remember CAP, the CAP theorem? So consistent, available, or partition tolerant. With consistent, I mean atomically consistent. So atomic consistency as in CAP. So remember that atomic consistency means that all machines will return the same results. Available means that the system continues to operate. And both of that in case of a partition tolerance. And of course, if the system just crashes in a way that is unrecoverable, if there is a partition of the network, then it's not even partition tolerance. So let's see what you say. So you say available and partition tolerance, and this is indeed the case. So the first thing is that it cannot be all three, right? That's the CAP theorem. And what it means is if you are partition tolerant, then you have to make a choice between being available or consistent when there is a network partition, right? Okay, so indeed, the idea is that, do you remember the vector clocks? When you have the vector clocks, it means that in case of a network partition, time is no longer a line. It's no longer just a linear timeline. It can split and fork into a dependency graph, a directed acyclic graph. And then you no longer have a total order between the versions of the data. And the moment you no longer have a total order, you become not consistent, eventually consistent, but not consistent. For whom is that clear? All right. And another system that would be consistent and partition tolerant, that would be that during the partition, it stops being available, but it will still recover when the partition is resolved. Okay. Here's another question for you. If you need to use HDFS and you want to create a directory, to whom do you speak? With whom do you communicate? The name node, the data node? Or for getting the actual data for a file, so the blocks, do you speak with the data node, the name node? So this is the question. So the first one means the data node for both of them. Then the second answer is for creating the directory, it's the data node. For getting the data is the name node. Or vice versa, or for both of them, the name nodes. You notice that here I use the lowercase name node, data node. It's very common, and I did last week, to use the camel case. That's because that's the node, the name of the Java classes. So this is why we tend to take them over when we call them. Let's see what you said. And we have a majority, and the majority is correct, indeed. So all the metadata is handled by the name node, which is the coordinator node on the top. And to get the actual blocks, the blocks are stored on the data nodes. And this is why they are called data nodes, because this is where the data is. What was left out of the question is that, of course, you need to know in what order the blocks should be assembled and which are the blocks for that file. And that is actually stored on the name node. Right? Okay, and finally, please answer as quickly as possible. What is the size of the order of magnitude of the size of a block? Quickly, that you should know now. I didn't start it, that's why. Yeah, now you can. Let's see it live. I want 100% here. Yes, let's see if it holds. Right. There was a question, by the way, on the Moodle forum that I answered to try to give the motivation. So basically, in fact, you could try to go ahead and implement HDFS. So install an HDFS cluster. You can do it with a few clicks on Amazon, for example, with EMR, Elastic MapReduce. And you can change the configuration and try to set the block size to 4 kilobytes. You can try, but then you will see that it's going to cause problems. And the same goes for larger partitions. So the idea is really that if the block size is too small, then as soon as you have a file that is like 1 terabyte, for example, 1 terabyte isn't that large, right? But if you have blocks of 4 kilobytes, then you basically are looking at 250 million blocks. And you have to imagine that every time you fetch a block, some software needs to be executed, right? Some Java code needs to be executed, right? So this is why it's very costly, and you should avoid having millions of blocks. So with 128 megabytes, you only have 8,000 blocks if they are that size for a terabyte file, right? And now the question that was a very good question is like, but anyway, physically on the disk, we do have the 4 kilobytes blocks, right? Because this block here is a file on the local drive. If you actually go locally and see the hard drive, it's actually a file. So it will be physically on the actual hard drive also 4 kilobyte blocks. But you have to remember that when you are looking at the hard drive, this is much smaller in size, so things are much faster. And actually fetching these 4 kilobytes is also optimized by hardware. So it doesn't matter that you would fetch 250 million small blocks on the hard drive itself, because this is highly optimized. But here, when you look at the scale of HDFS, the actual codes that would get an HDFS block is much more costly to execute. And then you get the latency and so on. So this is the idea. So the mental picture that you should have, imagine that you do it in a linear way, right? We will parallelize later. So it means you wait for the first block, download it. Wait for the second block, download it. Wait for the third block, download it, and so on. So you alternate between waiting for a block and actually sending the data. If your block size is too small, then the waiting time will be, it's a constant, so you will wait, and then it will immediately download the small block if it's a small size. And then you wait again and immediately download. So you spend most of your time waiting. If you make the blocks bigger, the waiting time is going to stay the same, but then every time you wait, you will download more. So you basically batch together the downloads if you want. It's like using a zip file when you upload to the server. So this is why when you have larger blocks, like 128 megabytes, then you're going to wait a little bit, but then it's large enough that then the downloading takes a lot of time in comparison to the waiting time. So it means that most of your time is spent downloading, right? And since the number of blocks is smaller because they are larger, then it means that the number of waiting time periods is also smaller, right? So what we want in HDFS is to spend more time downloading data than waiting for data to be downloaded. Then if you go even higher and have absolutely enormous blocks, then you'll see that you start running in other issues, but this happens more in parallelism, right? If you have huge blocks, you can no longer spread them over multiple machines to read them with MapReduce. So this is why it's not a good idea to go to that large blocks in the end. So 100 megabytes is the proper order of magnitude. Now, a word of warning, this is 2024. Things are evolving. The hardware is evolving. The properties of the drives and networks is evolving. What is true today might no longer be true in 5 years or 10 years, right? So in fact, Microsoft already is switching to higher block sizes. I think they are now at 4 gigabytes, right? It's kind of 10 times in terms of order of magnitude. So you see that things are developing, right? But 4 gigabytes, 100 megabytes, it's still kind of the same order of magnitude. This is what you need to remember, the ballpark of that. And maybe in 20 years, it will be so different that you need a completely new architecture. Because it could be that suddenly things become much faster over the network, much faster than on the hard drives and so on. For example, what some people are doing is that they put everything in memory, then there's no hard drives anymore, and so on. So you see that actually is evolving. All right, and some of you might actually design these future systems that will work on the new kind of hardware. All right, so let me now switch back to the slides. My goal was really to give you an intuition of why that is. Who would say you now have a good intuition of why this size of blocks? Right, okay. And you'll see when we do MapReduce and Spark, it will all make sense. All right. So the cliffhanger, the name node is a single point of failure. There's only one. If it crashes, we are doomed. So let's address this. So yeah, let's imagine it fails. There's a crash. What do we do? Maybe we restart it, right? So that's optimistic, right? It's assuming that we took our precautions and backed up the data in some way of what is there, but then we restart it. So what is there that we need to be careful to consider when we restart? So this is something we saw already last week. We have the file namespace. That's the whole bunch of directories and file names, you know, the file structure. With access control and so on. Then we have the mapping from the file names to the block IDs, which are just integers. And then we have the block locations. That is, for every block ID, you have by default, 3 data nodes, the IP addresses of the data nodes that have these blocks. Now, if you want to be resilient in case of a crash, if the name node suddenly crashes and you want to be able to restart it, you need to make sure that this is saved somewhere. So what do? Well, you put the file namespace and the mapping from the file names to the block IDs to a file on some storage. I'll tell where in a few seconds, but we need to store this information about the file tree and the mapping from the file names to the block IDs. Who agrees that if we lose that information, we cannot do anything anymore with the data? Who sees that? The blocks alone are not enough. Right? Because you wouldn't know how to glue them together anymore. This is how to glue the blocks together. It tells you which blocks belong to what file. So we need to store somewhere to persistent storage this information that's called the namespace file. It has the whole file namespace and mapping to block IDs. Why do we not need to persist the third thing, the mapping to the data nodes? Why are we not saving that? Yes? Exactly. This is in the block reports. So you would anyway just request block reports when you restart, and then the data node will tell you which blocks they have and that you can rebuild, right? Who agrees? Okay, so we can save ourselves the backup of this. Now, what kind of persistent storage? Well, typically, at least in the early versions, it's a network attached drive, NAS, right? So you basically store it on some storage that is shared over the network because it might not be the same machine that you restart a name node on. So you put it on network storage. You just need to be aware, because that might be something that comes to mind. Is this stored on HDFS? No, of course it's not stored on HDFS, because then you have a bootstrapping problem, right? Because if you store it on HDFS, but you lose the ability to read from HDFS, you wouldn't be able to read it. Who sees that? Right? So it needs to be outside HDFS. So we put it on some network drive that can be read independently of HDFS. Now, here's the thing. We might have done some backup, but then the system continues to run. And so we might have added files or modified or appended to files and so on. What do? Well, here it's more efficient to not save every time a new namespace file, but instead we store a second file that's called an edit log, and that's really a journal. It's all the updates in the order in which they were made, like a blog, right? You keep a journal of every modification. Here I created a directory, I added this new block with that ID, I deleted that file and so on. It's just a journal. For whom does that make sense? Right? And we just keep appending to the edit log like this, okay? And it grows and grows and grows as time elapses, right? Now, you probably don't want to keep it only on the network drive. You probably want to back it up as well, but for this, you can put it on some other drives, to some backup drives, maybe some tapes, to cloud storage or Glacier and so on. All right. So then you have even copies of that. Now, if we've done that, and it's on the network storage, plus it was backed up, if it fails, now we have the answer. We restart it, right? How much time do you think it's going to take to restart it? Who thinks just a few seconds? Who thinks maybe half an hour? Who thinks an entire day? Okay, so you are in the right ballpark. So most of you said half an hour. It is indeed roughly half an hour. Because what has to happen, so first you need to reboot the system and so on, but you also need to reread that and reinstantiate all the memory of the name node, right? So first what you need to do is take the namespace file, so that part here, and you just read it into memory. So you have the file namespace and the mapping and so on. I didn't put the file namespace, but it's in there too. And then you play the edit log. It's who has already seen a MIDI file in music? It's like playing the music from a MIDI file. A MIDI file contains all of the notes that you play. It's like a journal of the music you're playing, and you play it. It's called a sequencer when you do that. Well, here it's the same thing. We read through the journal, and we apply every creation of a directory, adding a block ID and so on, and we just play it like this. I put this little play here to basically say that this is what's happening. And then you basically bring that snapshot. So the namespace file was a snapshot in the past, and then you play the latest edits, and now you are in the latest state. But then you also need to wait, as one of you said, for the block reports of the data nodes and until they connect to you, and then you can actually infer the block locations. And after half an hour, then you're ready to actually serve as a name node. Okay, for whom is that clear? All right, perfect. So this is why it takes a bit of time to start it up again. Can we do better? Of course, the answer is yes, because otherwise it wouldn't be very fun to study. So the first thing that we can do is, since we notice that the edit log takes time and that the more time elapses, the more time it will take to actually play the edit log, you can periodically rebuild a new namespace file and start again with an empty edit log, right? You just take a new snapshot like this, that it's a bigger namespace file, but then there's no edit log anymore. You just load that into a memory and you're done. And then you again create a new edit log starting from 0. For whom is that clear? All right. So now there have been a few modifications to the system after the years, because that's already more than 10 years old. I will tell you what the latest state is of the system, what is right now implemented in order to mitigate that. What happens is that we will have more than one name node. One name node is the active name node. That's the one that is in charge of reading and writing. So that's the one that we've studied last week. But we have more name nodes that are called standby name nodes. These name nodes do absolutely nothing except keeping track of the state of the file namespace and the block IDs in exactly the same state as the active name node. But they do not process any reading or writing requests, right? They are just a mirror of that. Now, the way they do it, let's talk about the case where you have the namespace file and edit log in the network attached storage here. Then what they do is that they read the namespace file and the edit log, and they do what's called tailing the edit log. It means that they keep, tail is a command, right? If you want to see when a file is a log that you append to, you can use the tail command and see the end of it, right, as it goes. So you tail the edit log, and so these ones basically look at the edit log and keep implementing the changes that are ongoing at the same time, maybe with a slight delay behind the name node, right? And so here, they should have exactly the same information. What's more, all the heartbeats and the block reports are not only sent to this active name node, they are also sent to the standby name nodes. So it means they also know the mapping from the block IDs to the IPs of the data nodes. right? So in here, you have all three components of what's in the brain of the active name node, the file namespace, the mapping from file names to block IDs, and the mapping from block IDs to data nodes. For whom is that clear? Right. And so now, if the active name node fails, you just promote one of the standby name nodes to be now the new active name nodes, and that's much faster because they are already ready. They already have everything it takes, right? And in the meantime, in the background, you can restart this one and just turn it into a standby name node. Okay? Now you have a different way than the network attached storage for storing the namespace file and edit log. It's called the Quorum Journal Manager. I will not say much about this, but the idea is that you have journal nodes. Journal nodes, it's a lightweight process, just like the name node and the data nodes are processes that run on machines. You have the journal node. And you need basically a majority to agree on an edit log and namespace file. So for this reason, you need an odd number. You know how it is when you create a committee and you need a majority, you pick an odd number. If it's an even number, there's a risk of having a tie. So an odd number of journal nodes, typically you make them run on the same machines as the name nodes, active or standby, but it can be 3, 5, 7, and so on. And so that's called the Quorum Journal Manager, and then they just will agree on the latest version of the namespace file and edit log. It's an alternate method. So this here is called high availability, HA, high availability. And this was implemented in order to make sure that it doesn't take half an hour to restart. Yes?
Why do we want to run Quorum Journal Manager on the same machine as the name node? Because if that machine crashes, the journal manager will be gone too.
Absolutely. This is exactly why the way that the journal managers are designed, so the Quorum Journal Manager is designed, is that it continues to work if there's more than half of it still alive. For example, if you have 7 of them, you still have 4, that's enough to continue to function, right? So this is the reason. You should have at least 3, basically, to be safe. But it's also resilient to crashes. This is really the nice feature of the Quorum Journal Manager. And quorum really means majority. It's whichever majority you have is enough. Does it answer your question? Awesome. Okay. Now there is something else. It's a third type of name node. So standby active, there's a third type that's called observer name node that also is available. An observer name node is kind of a standby name node plus plus. It's basically a standby name node, but it's authorized to serve read requests. So if people want to read something from HDFS, they can connect to the active name node, of course, but they can also connect to the observer name node. And the observer name node will be able to give them the information, so the block IDs, the data nodes, for reading data. So what's very important is that for writing data, it's always the active name node that takes care of it. But the observer name nodes have the right to also serve clients with read requests, right? So you have standby name nodes, observer name nodes, and the active name nodes. Okay? For whom does that make sense? All right. Now you might see in the literature, if you Google around or ask ChatGPT, you might hear of checkpoint name nodes or backup name nodes or secondary name nodes. You can forget about that. It's history. That's basically the intermediate implementations before we had the current version. It's basically the ancestors of the standby name nodes, right? So you don't need to know anything about checkpoint backup and secondary name nodes because now there's just standby observer and active name nodes. Okay? Very good. Now there is another feature. So this is high availability, it's called. We have another feature that's called the federated DFS, federated distributed file system. It's basically exactly in the same way as when who already installed Linux. Do you remember that? I don't know if it's still today, but back then when I tried, during the installation, you can create partitions and then you can allocate the partitions to some paths. Like there's a partition for slash, one for /root, another one for /home, and so on. Do you remember that? You can do the same thing with HDFS. You can basically allocate your file system to some directories saying, I have a name node that is responsible for this part of the file's namespace and another name node that's responsible for this one. So I did it with /foo and /bar. The way that works is that depending on what files you want to read or write, you're connecting to the right name node that has that covers the directory you're interested in. But basically, these two do not even communicate, right? It's really like as if this was a name node of its own on its own cluster, and another name node of its own on another cluster, except that they share the data nodes. But you can imagine the data nodes, they just have blocks, right? So sharing them is no problem at all. You just put all the blocks spread all over the place and that's it, right? You just have every block ID that is in either one or the other. For whom is that clear? Right? So this is called the federated HDFS, federated file system, where you have multiple name nodes. So that also helps to scale up a little bit if you want to process more data. Okay. So that was the single point of failure, the way we address it. Now, how does it feel to use HDFS? Well, in fact, you can use it on the command line in a way that's quite similar on what you do on your laptop in the command line, when you create directories or cat for seeing a file and so on. The way it looks like is that you have a command that's called Hadoop FS. And then let me show you here, Hadoop FS ls, Hadoop FS cat, Hadoop FS rm, Hadoop FS mkdir. These are basically this is the POSIX standard. ls, cat, rm, mkdir, these are basically commands that you have. Who knows them? Most of you, right? So the way you use them is you just put a dash in front and you put it after Hadoop FS. And when you do that, this is going to be working on the actual Hadoop file system. There is one difference, is that when you press return, it's going to take 1 or 2 seconds to actually respond. So it's much slower than when you do it on your own laptop. But of course, you're communicating with a huge cluster, right? So just that you're aware that there is some latency here of 1 or 2 seconds. What's really nice is that this program here doesn't just work with HDFS. In fact, it will also work with your local file system. If you use the file, so you know the file scheme, file colon, blah, 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 it's to the local file system. It also works with S3. You can also connect to S3. There's special S3 URLs for that and so on. So you can connect to multiple places. And the way it works is that the underlying command is actually called HDFS, but this one is hidden. And instead you use that command that depending on what you put in there, it will either do it locally or on HDFS or on S3 or on any other system. So it's very, very convenient. Okay, so basically the idea is that these are URLs just in the same way as in the REST API. The scheme is just implicit. So if you don't say anything, by default, typically it's HDFS. So they actually start with HDFS : / and then the host and then the path. But in order to not have to type that URL every time, it's convenient to just put / with the root of the HDFS system. And somewhere else, you specify that by default, this is HDFS on that host. For whom is that clear? Right. Awesome. Perfect. So you can actually try that out if you, yes, go ahead.
When I have when I have a separate name node in the federated DFS for the sections foo and bar of the namespace, how do I handle creating a new section, for example, foo bar? Does it just randomly assign it to one of the 2 name nodes, or do you start a new name node?
No, I think that in that case, so I'm not very knowledgeable specifically on federated HDFS. What I would say is that if you're not the system administrator, you probably cannot create a new directory if it's not already handled. Or it might be that there is a mechanism that says everything else goes there, right? So foo is here, bar is here, and all the rest would go to that one. That is also a design possibility. But I don't know what design decision they made. We would need to look at the documentation, right? I'm not sure if I actually answered your question, or maybe it's a disappointing answer, but yeah, that's what I would assume. Yeah. All right. Thank you. Any other questions? No. All right. Yes.
I wanted to ask about the federated shape. If we're working with this, the file 1 and file 2 under namespace foo, are these separate files from file 1 and file 2 under namespace bar? Like this is not duplication that's going on?
Oh, yes, exactly. There's no duplication here.
Okay.
It's just this example happens to give the same names to the file because I didn't have a lot of imagination when I did the slide. But this is really not a duplication.
But
This is-
duplication could happen. Like there could be multiple name nodes that are like duplicating the same content
You
within one part
could.
of the federation.
You
Okay.
could. But the question is it a good idea? Because you already have replication with the blocks, right? You already write every block 3 times. So if you want to replicate, it would be maybe a better idea to increase the replication factor rather than to bother trying to mirror the data. However, you could imagine mirroring across data centers. You could have some architecture that makes sure that what there is in the data center is regularly mirrored with another data center, right? It's actually a common thing that companies do to have a mirror of their database somewhere else, maybe with a delay, right?
I also wanted to ask about quorums and voting. Each individual vote, I may have just misunderstood this. Is each individual vote one name node, or what is the unit that we're talking about here?
The journal node. It's called the journal node, but it's very common to put them on the name nodes. So again, I repeat for the case that it wasn't clear, I tend to say name node or name or data node to designate the machine, but it's really not a machine, it's a process running on a machine, right? And on the same machine, you might have other processes. So these machines here at the bottom, they run a data node process, but we will see later that they also run other processes for MapReduce and Spark and so on. So that's not just the data node process. But when we speak, it's convenient to just say the data nodes, the name nodes, because it's faster to speak in this way. But always keep in mind, we're talking about the process. And so basically the journal nodes, they are also processes. So there is a journal node process, but it's running on the same nodes as the name nodes typically, right? It's very lightweight, doesn't take a lot of memory or power. So you just put it on the same nodes as the name nodes.
Thank you.
Okay, thank you. Another question, I think I saw a raised hand. Yes, over there. Yes, you can try. If I hear you, I'll repeat.
And we want to have an observer name node. Do we have one observer per, let's say, a sharded name node, or does the observer track both?
So I was wondering the same, actually, and I didn't find an answer. I read, maybe you find it. I read through the documentation. There will be a link in the lecture. So if you look at the documentation, then they have one page on high availability, as if federated didn't exist, and they have one page of federated AGFS, as if high availability didn't exist. So they don't say. However, I can make a guess. That's all I can do. So my guess is that since the idea is really that the two name nodes are running independently of each other, I would assume that we have a whole bunch of standby observer and active name nodes for one on the left, and another bunch of active standby and observer name nodes for the one on the right. That is my guess, right? Does it make sense? Right. All right. Other questions?
There's one question on Zoom again.
On Zoom, yes.
Would every name node in federated DFS have knowledge of all the block allocations on the entire architecture in order to use that knowledge in the case of a crush? Or
That
is the-
yeah, that's a
or-
very good point. Go ahead.
Or is the name node metadata atomic and separated? And
So this is basically related to your question, right? If you think about the architecture you want to have, that would be a second guess, right? A second guess could be that you have a way that this name node on the left could be an observer name node, or maybe a standby. I would say, why not an observer, but a standby name node for the other one. So basically, this is the active name node for foo, and the standby name node for bar, and this is the active name node for bar and the standby name node for foo. You could also imagine something like this. You basically use the same machines. This is also, that's a second guess, makes a lot of sense too. So that could also be designed in this way, right? What I don't think is happening though, is that you would have an observer name node that has everything, because the whole point is to split it, right? But I could imagine that you might consider reusing the processes. Right. Okay, any other question?
Does the client know about all the name nodes? For example, if there is federated DFS or like when we switch to another name node because one crashes, because it's hard to track. Maybe there is a name node for name nodes as well.
Absolutely. So here too, there could be, I'm thinking out loud, right? About if I were to design this. I can think of two different designs. The first design could be to take literally the fact that this is really a name node as if it were alone, and this is a name node as if it were alone, so they are not aware of it for each other. Then I would push the burden to the clients. It's basically the client that has to know. Basically, the Hadoop commands would have to know to whom to connect. This could be one way. A second way would be to try to make these extra smart so that they are aware of each other and can redirect. I don't know which one was taken. I would maybe think of rather the first one because of the way they formulated, saying they really are completely isolated. But I could imagine these two designs. It's a little bit, if we were basically to redirect, it's a little bit like what happens in Dynamo, that they are able to redirect to each other, the requests, right? So again, the way I answer this question probably is a pattern, right, of the design, is that the engineers that designed the system, now I'm giving you directly the results of what they did, right? But when they actually did it, they had to think in this way. They had to consider all the possibilities and then make a decision. Sometimes it happens to be the right decision. Sometimes another decision would have worked just as well. Sometimes somebody actually tries another decision 5 years later and finds out that it actually works better, right? So what I want to communicate is really two things. First, that you know how it's been done, because then you're aware of the mistakes that have been made, but at the same time, that you're able to also think by yourself, put yourself in the shoes of these designers and ask yourself these kind of questions, right? So what's important is not so much the answer that I'm giving you, but the thought process behind the answer that is more important. Does it make sense? Awesome. Okay. So these are the comments, basically, when you connect from the client, and you have extra comments that don't actually exist locally. It's copy from local and copy to local. It's basically how you upload a file that is on your file system. You upload it to HDFS, or how you download a file from HDFS to your machine. Of course, if you download a file from HDFS to your machine, this is assuming you have enough disk space. Right? You would not do it if the file is actually enormous and larger than your drive, which is absolutely possible. But this is a common thing to do when you have a data set that you would like to process with MapReduce. You might have to use the copy from local command in order to just put all the files there. HDFS or S3 or any other file system. Another way of doing that is to use the UI. You can also just connect to the S3 UI and upload from there, right? So there are many ways. The shell, the UI from a computer program in Java, there's many, many different ways. Or the REST API too. Yes?
Something like local screen to local. You want to say completely run tablets or something like that?
Yes, absolutely. You could imagine streaming some file to HDFS. In that case, you probably would not be using this command here, because this command is convenient when you have a file that already exists and you upload it. But you could imagine using a Java program. You write a Java program that uses the HDFS API and that creates a file and creates blocks, but it just makes up the bits on the fly. You could absolutely do this, because to HDFS, it doesn't make a difference. Through the API, you just need to send bits, right? So whether the bits come from the local disk or whether you just compute them on the fly, that doesn't make any difference. In fact, when you have logging, like you append and create a log, that's exactly what's happening, right? And that's also what's happening when you write from HDFS. You just make up the data as you compute your MapReduce job, right? As we will see later, right? Does it make sense? I could imagine that there's a way to hack the whole thing by copying from a file that you append on the fly and so on, but that's probably advanced IT, and it probably would be easier to just write a Java program, I feel. Okay? Okay, then that's because you're computer scientists. I'm not scaring in big data for engineers. I'm not scaring the students of other departments with this. But basically, you have some configuration files that you can find on the machines on your cluster. They are well hidden, but you can find them. And there is a place, for example, where you can say the default is HDFS host 8020, for example, if that's the name node where it is and the port of the name node. HDFS scheme, it's a URI, that's going to be prepended to every one of these. So in front of this, you always have HDFS, blah, blah, blah. You can change it. You can set S3 instead of that, or file for the local file system and so on. You can change, but that's basically the default. If you don't specify a scheme in your URI, just slash, it takes the default from the configuration. By default, the default will be HDFS, of course. All right, and something fun to do, actually, if you want to explore and create a cluster somewhere with a few clicks, and if you find out where the local directories for the name node and data nodes are, then you can SSH yourself to the actual machines and go and see the files. If you go here, for example, you look for the data node named here and log yourself by SSH onto the machine on which there is a data node, you will see the blocks. You will see the actual blocks that are actually local files. Does it make sense? For whom does that make sense? All right, awesome. But this is really for the ones who are curious and want to see what's happening behind the scene, because the actual users wouldn't actually bother with this. Okay, then I just wanted to issue a warning about the vocabulary, that the words might change. In GFS, they don't say block, they say chunk. They don't say data node, they say chunk server. They don't say name node, they say master. They don't say namespace file or FS image, they call it checkpoint image. Edit log, they call operation log, and so on. But that's okay, right? It's just terminology. It's just like using another language. Terminology is still important. It's important when you communicate with other people, that if you use the same word, it makes it easier. But it's good to have the flexibility to use other words to mean the same thing, right? So this is the idea, just be aware of it. And by the way, block, chunk, I'll have so many others during the semester: block, chunk, split, shard, partition, and so on and so on. There's many other versions of that, okay? And the other aspect is that when I say 128 megabytes, that's an order of magnitude, right? So the original one had 64 megabytes. There's also flavor of HDFS, by the way. There's Cloudera HDFS, there's Apache HDFS. It's actually just like Ubuntu and Debian and all the flavors and distributions of Linux. Then you also have the distributions of HDFS like this, and they might have different defaults, okay? And that's pretty much it with the distributed file systems. Do we have any other questions? Anything you want to know? On Zoom? Nobody? Do you want to have a break?